Okay, here we are in day 2 of 11.1. We're graphing radical functions, and now we are going to do a little bit more to the radical. You did have the opportunity to look at how adding something to the radical expression changes things in your assignment, but we didn't do it in our notes. So, having done this in your assignment, this -2 is outside of the radical. What is your prediction as to the transformation of the parent function? It's a very fancy sentence. You know what I'm saying? What will happen to the parent function when we subtract 2 on the outside of that expression based on what you did yesterday? Kate?
Translation of negative.
Very good. She says translation down 2. We need to kind of say a vertical translation because we can have a horizontal translation too, left and right. This is going to be a vertical translation, -2. How will you graph this function, John?
You would plug in, you make a table, and for x you would put 0, 1, 4, and 9.
So we are still going with perfect squares because the expression inside that radical is just x. So when we take these roots, we want perfect squares in the radical. So what do you get, John, when you have square root of x when it's x is 0? 0, square root of 0?
You get a -2.
Good. So it's 0 minus 2, right? And so how about when we stick in 1? Square root of 1 is
1. So
minus 2.
-1.
Good, -1. And how about when we plug in 4?
0.
Good. And 9?
1.
1. Good. Okay, so don't forget, we're comparing these to the parent function, so let's put the parent function 0, 0, 1, 1, 4, 2, and 9, 3. Oops, it's not as exact as it should be, but I'm a little uncalibrated, so. Okay, so our new function is at 0, -2, 1, -1, or 0, 9, 1. Okay, so let's describe the domain and range of the new. What is the least value that x is here, Oscar?
0.
It's still 0, so how would you describe it?
X is greater or equal to 0.
Good. The y values now, Matthew.
I did y is greater than or equal to -2.
Good, so we have a different range here. So hopefully in your assignment, when you saw this type of transformation, you realized the domain and range might be different. In this case, the range is different because the whole thing has dropped down 2 units on that coordinate plane. Okay? And so if we want to describe the transformation, it's exactly what Kate said. It's a translation. It's actually a vertical translation, right? -2, down 2. Very good. Okay, any questions? In this case, we're changing the expression inside the radical. This is totally different than adding something outside the radical. So, did you face any of these in the assignment last night? Inside the radical? Okay, so let's see what is different now. Okay, so again, I mean, we need to have a table of values so that we can find this function on the graph. The difference is the radical expression is changed, right? What's the smallest value that we can take a real root of? The square root of what, Jack? 0. So now if you plug 0 into this, x is 0, what really is inside this radical? 2. So, and that's not even a perfect square. So we could find the square root of 2 and take an approximate value and graph it, but it's not as easy as a perfect square. How could we make that expression in there be 0? Cassandra? Very good. So -2. So -2 is the smallest value allowed in the radical in our domain now, right? Because -2 plus 2 is 0. And the square root of 0 is 0. So we get a 0 out when we plug in a -2. The next perfect square that we like after 0 is what?
1.
1. Sometimes we forget that one. But what value would we plug in here to make a perfect 1? Negative 1. So we're going to plug in a negative 1. This is a different domain, isn't it? And we do it because negative 1 plus 2 gives us the square root of 1, which is 1. And then the next perfect square we want is 4. So the next value we'll plug in is 2. Now you don't have to choose these values. You can find the square root of 3 if you want, right? But this first value is really critical, that you know the smallest number that could be input. You've got to find that point. The rest of them are just going to form your curve, right? So, but if we do plug in 2, we get square root of 4, which is 2. And the next number that would make a perfect square in that radical is 7. So the square root, when we say the square root of 7 plus 2, it's the square root of 9, which is 3. And this is the principal root, because outside of that radical is not, there is no negative. So we're looking for the principal root. Okay, so we plug these in and compare. So negative 2 is at 0. Negative 1 is at 1. 2 is at 2. And 1, 2, 3, 4, 5, 6, 7 is at 3. So if we compare that to the parent function, which is always at 0, 0, 1, 1, 4, 2, 9, 3. I guess let's talk about the transformation that just took place. The transformation is? It's a horizontal translation, right? Or translation left by how many units? 2. So we could say a translation left 2 units, right? Or a horizontal translation negative 2. Is there any vertical stretch or vertical shrink? Nope. And so where would you see a number in the equation if there was a stretch or shrink? Like in front of the radical, right? Like multiply in front of this radical here something other than 1. There's a 1 there right now, that invisible 1, right? Okay, and then let's talk about the domain and range. The domain has changed, right? What's the smallest value that we input here? Negative 2. And then did we put values in less than negative 2 or greater than? So x's are greater than or equal to negative 2. And the y values start where? Still at 0, right? And do they get greater than or less than that? So it's still that same range that we've seen. Okay? Well, actually that changed with the value on the outside of the radical. Okay? Do you think it would be possible for us to shift it left and move it up? And stretch it and reflect it and everything else, right? Combo. Okay, so let's try that. Let's try doing 2 things and then we're done today. Almost done. Okay, so this is fun because we don't just have one thing. We don't just have 2 things. We have 3 different things happening to this radical function, right? So we have a 2 in front of the radical. And so what do you anticipate that will do? How will that transform the parent? Stretch, right? Stretch. Okay, and then we have a negative 1 in here, or we're subtracting a positive 1, depending on how you look at it. What way will that shift this? What's the smallest x you could put in here? 1, right? So it shifted this which direction? To the right. Okay, and do you notice in the model here that we're subtracting h? So if h is positive, we're shifting to the right. We're going positive. And then the k in this case is a 2. That's a 2. And so that's going to transform it which direction? Or how? No, the stretching was out here. This is a translation up 2, right? Vertical 2. Okay, so we have a stretch, translation to the right, translation up. Okay, and we can find that by inputting points. So we said the smallest value that you could put inside that expression, the smallest value it must equal is 0. So the number that we're going to put in is 1. That's the smallest value. Now that gives us 0. What would give us 1? 2. 2 minus 1, right? And what would give us 4? 5. And what would give us 9? 10 minus 1. So these are the values we want in the domain. So let's go put our domain down. The x's need to be greater than or equal to, 1. And then let's see what happens with y's. When you do plug in 1, you end up with 1 minus 1, which is square root of 0 is 2 times 0 is, and 0 plus 2 is 2. There it is. When you plug in 2, you have 2 minus 1 is 1. Square root of 1 is 1 times 2 is plus 2 is. Plug in 5. 5 minus 1 is 4. Square root of 4 is 2. 2 times 2 is 8. 2 times 2 is 8.
Oh, just kidding.
4 plus 2 is 6. What do you predict? Look at this thing. What do you predict the next number will be? 8. Because we're going up by perfect squares. We're not increasing the domain by 1 though. So that's where we do not have a linear equation here. It's a radical. Okay. So 10 minus 1 is square root of 9 is 2 times 3 is plus 2 is. Yay, it's exactly what we thought. Okay. So plug in 1, get out 2. There's your starting point. Plug in 2, get out 4. Plug in 5, and out pops 6. Plug in 10, and out pops 8. The smallest y value. Look at your table or look at your graph. The smallest y value is 2. So the values are getting greater than or equal to 2. And your transformations. Based on this 2, we have a vertical stretch. Based on this, we have a translation which way? This one changed to x, right? Right one, to the right one. And based on that 2, we have a translation up 2, right? Up 2. Or a vertical translation, positive 2. Okay, so this is just a summary box to note how a radical function is transformed by multiplying or adding things in various places, right? Here is the model of the possible areas that we can impact the function, right? So the first thing is the parent function starts at 0, 0 and passes through 1 and a from the model function. And we have a horizontal translation based on h. If h is positive, we go right and left if it's negative. But remember, we're subtracting h. This is always a little bit confusing when you're subtracting the term. And then the k shifts, translates it up or down. This is easier because it's plus k out there. So if it's plus 2, it's up. If it's minus 2, it's down. It's easy. Okay? So here is, in my own terms, kind of what happens. We can stretch and shrink and reflect it based on our a, just as we've done with all of our other functions. We translate left or right with our h, and up or down with our k. So this is the assignment for day 2.